Hello students! Today we're going to be talking about Stanovich Chapter 5. It focuses all on correlations. So how do we interpret correlations? All sorts of things about them. The first thing, and one of the most important things I hope you take away from this lecture, is while this is labeled correlation and causation, I do want you to know that correlation does not mean that there is a causal relationship. So correlation does not mean causation. It's the end of the lecture, all done. You can go to chapter 6 now. No, I'm just kidding. We're going to, just kidding about going on to chapter 6 now. We are going to talk a lot about correlations. So we've mentioned them before. So essentially a correlation is when you compare the relationship between variables. So a lot of our example are going to be just two variables and the relationships between those two variables. So here's some examples of correlations. This is a graph of a strong positive correlation. So variable 1 would be down here, variable 2 would be here. So if you're about midpoint in variable 1 and midpoint in variable 2, your dot would be about there. So that would be, could be purpose score and happiness or something like that. Would look like that. So here, this is called a negative correlation. Negative correlation doesn't mean like it's a bad correlation. It's like math terms. Positive is adding to, negative is taking away. So strong positive, the relationship is going up towards the right. Negative, it's going down towards the right. So this doesn't mean that it's a bad relationship or it's a weaker relationship or anything. It's just the direction. So positive and negative are about the direction. So this is a strong positive correlation, and this is a simple positive correlation. You can see there's a little bit more spread out points here. The relationship is stronger here because it's closer to a direct line than this one. And we'll show some actual examples of real data and what the real data actually looks like. This is an example of no correlation. There's not really any line of best fit through this. There's no negative relationship. There's no positive relationship. Some people who score high on variable 1 score high on variable 2, but some people who score high on variable 1 score very low on variable 2. So that's where those are marked. So let's look at maybe the relationship between happiness and scoops of ice cream. Which one do you think this might be? My guess is you'd probably have a positive correlation. You get 1 scoop of ice cream, you'll be kind of happy. 4 scoops of ice cream, you'll be pretty happy. And 5 scoops of ice cream, very happy. So this is your ice cream variable down here. This would be your happiness variable over here. So when you have 5 scoops, let's just make it easy, 10 scoops of ice cream, your happiness score is also 10. 5 scoops of ice cream, your happiness score is also 5. So that would make sense. I would suspect that. But it could be a negative correlation. Maybe you get 5 scoops of ice cream and your happiness score is still 5. But when you get 10 scoops of ice cream, your happiness score is now 0. Or maybe you get only 2 scoops of ice cream and your happiness score is 8. So you see, we've got 10 ice cream scoops related to maybe 1 happiness point, 5 and 5 right here. 2 scoops of ice cream related to maybe 9 or 8 happiness points. So correlation is not causation. This is an interesting correlation that we find. There's a fairly, I don't remember from this if this is the actual data on it. It may just be an example graph that I put these labels on. I can't remember, but this is a study that has been done, is looking for, is there a relationship between number of ice cream sold and the murder rate? Well, it turns out there is. So when you have more ice cream sold, you also have more murders. When you have very few ice cream sold, you also have fewer murders. So is selling ice cream causing murder? Is murder causing ice cream sale to go up? No, obviously not. That would be absolutely ridiculous. But they are related. They are related variables. Or another way to say this is they are correlated or they are associated. They are connected in some way, but that doesn't mean, and that way might just be mathematically. There's just a relationship there. But that doesn't mean that one is causing the other. So ice creams is not causing murder. Murder is not causing ice cream. But they are correlated. There is a relationship. In this kind of case, what do you think it might be? what is causing this relationship to exist? Because it is a true relationship. Again, I don't remember if this is the actual data from a study on this, but this relationship does exist. It is a positive correlation. So actually what's happening here, we'll talk about it in a minute in more detail, but there's a third variable, heat. When people are out during the summer, when it's warmer, there tends to be more murders during the summer when it's warmer. There also tends to be more ice cream sold when it's warmer during the summer. So the same days that there's more murders tend to be some of the same days there's more ice cream, versus in the middle of the winter, not as many murders happening, not as many ice creams being sold. So there's a third variable in this case affecting both of these. So as people, we might expect a causal link between our variables, and we might have a bias that one thing is causing another thing. Maybe we really hate ice cream and we really expect that ice cream is definitely causing murders to happen. Or we might be misinterpreting our stats based on preconceptions. So here's some other examples of things that are related but not causally related in the same way that these people are making the assumptions. So let's read these couple comics really quick. I'll just be quiet so you can read them. So these do show more than just correlation causation problems, but this does give a good example here. They're related variables. Yes, everybody who has gone to the moon has eaten chicken, but it doesn't mean one causes the other, right? Here, they're making an error of what direction is the causal behavior happening. What's really happening, right, is they get to choppy air, then the plane gets bumpy, then they turn on the sign so that people will turn on their seatbelts. So this child is making the error that it's actually going the opposite way, that the sign is making it bumpy. So some errors there in what direction there's causationally, and then also an error here of, well, is there even a causal relationship? And no, there is no causal relationship in this one. So correlations can point us to the direction of causal relationships. Almost always, if there is a cause, they will also be correlated, but just because there is a correlation does not mean that there is a causation. So correlation does not equal causation. Hopefully I've said that enough points today that that's in your head and stuck with you forever. I'll say it a couple more times as we go, so it'll hopefully get even more stuck. So here are a couple examples of real correlational relationships from some of my data from testing the heroism scale that I created. So as you can see here, some of these columns, each of these points is literally a person's score. So on this axis, we've got social responsibility. On this axis, we have empathy. So someone in my sample scored about a 3-point something on social responsibility. Scored a 3-point something on empathy, but scored basically, it looks like a 1.2 or so on social responsibility. So about a 3 on empathy, about a 1 on social responsibility. So that was their point. This person's point over here, this person scored about a 4.5 on social responsibility, but almost a complete 7 on empathy. So that's what each of these points is. Each of these points is a graph of the two variables. So jumping down, my cat just jumped on the table. Sorry. So let's go to this. Let's go to this one. It's a much bigger, broader correlation here. So you can see there's some people in this group that scored very low on both things. So this is actually the heroism scale. So scored basically 1 on heroism and basically 1 on self-efficacy. There's also some people who scored 1 on heroism, but 7 on efficacy. So see, there's a couple people right there, a clump of dots. So what the program does, what the statistic does, is it tries to find this red line. It says, hey, what's the line of best fit? Does this look like it's a positive relationship going that way? And all of these are positive correlations or very weak to no correlations. But you can see this one here is a very, very strong positive correlation. Very narrow data in a nice smooth line, really clearly going up that way. So that means it's a positive correlation. If it was flipped the other way, it would be a strong negative correlation. So if you flipped that data pointing from the top left to the bottom right, that would be a strong negative correlation. And the reason this is so strong, in fact, this relationship is, I think, one of the strongest on this diagram. It's actually a correlation of 0.94 because it's correlating the entire heroism scale with a subsection of the questions. So half of the questions are correlated with all of the questions. So this measure includes the 4 questions used for this measure. So it absolutely should be that highly correlated. It's half of the same data. So that's not actually how I would use those correlations, right? But since I'm putting them all in the system, it's saying, I'll give you correlations for everything. The computer program doesn't know that this is actually, these 3 are pieces of the same scale. What I'm really interested in is basically from here and above. So this is heroism correlated with moral courage. It's a pretty strong correlation. You see it's kind of wide, but it's very clearly going up those directions, and it is a correlation of 0.79. So that's a pretty strong correlation between moral courage and heroism. So that's that one right there. We can look at this one, the correlation between empathy and courage. So this one is the graph. We can see, yeah, there's some people that score very low on heroism and very low on empathy, but there's also people who score very low on heroism and very high on empathy. So this is a person with a score of about 7 on empathy and about 1 on heroism, versus this person up here scores about a 7 on both heroism and empathy. And this person here is scoring about a 4 on each. Right? So it's found a line of best fit. The data here, the correlation is 0.40. So still a positive correlation, but a lot less strong than this one here that we were talking about, the moral courage one. So this gives you a couple examples. Essentially what you can look at here is these 2 variables are graphed here. The actual number stat is here. So this is heroism and self-efficacy. This is their graph. This is the number. So very low correlation, pretty weak positive correlation, but it does exist, right? There is a relationship there. But that relationship, you can see, is much weaker, less pattern to it than this relationship, right? There's a very, very clear line through there, very strong relationship. And that's what the stats do when looking at correlations. We're comparing these 2 variables. So I compare empathy and social responsibility. How are they related? Well, they're very related. Their relationship is 0.63. I can compare social responsibility and moral courage, or social responsibility and self-efficacy. That one's right here. Right? I can compare social responsibility and heroism. That's right here. So, and then the number is right here. So this is what the graphs actually look like. So that goes back to these examples here: positive correlation, negative correlation, no correlation. And this is some actual data to hopefully give you a better sense of what these actual correlations really look like in real life. One thing I didn't mention, you can see here some of these scales have a very normal distribution versus some of them, like empathy. A lot of people scored a 7 on empathy. Most of the sample said they were very highly empathetic, basically, and fewer people scored low. So it's a little bit skewed this way versus this one and this one are much more normal distributions. Generally, that's what we like. We like to see a normal distribution for our scales. But that's another point. The main point here is that correlation does not mean causation. So having a correlation between social responsibility and empathy does not mean that empathy causes social responsibility or social responsibility causes empathy. Right? They're very related. They're probably developing maybe in similar ways in this case, but not all variables that are correlated are actually really related to one another directly. So a really good example of that is the 3rd variable problem, where another variable can explain the relationship between your 2 variables. So this is a problem when you haven't measured that 3rd variable. So here we talked about ice creams being sold and the murder rate. The third variable here is heat. Heat explains this relationship. It's a third variable that affects the other relationships. Another one was interesting that was seen, and again, I don't think this was the actual data. I think this is just an example correlation that I put into this slide. In the 30s, we saw that when there were times of fewer weddings, we had higher men's suicides. So on times when there were lots of weddings, so this is weddings right here, so lots of weddings, very few, if any, men's suicides. When there were very low weddings or no weddings, there were a lot more men's suicides. So were the weddings causing the suicides or the suicides causing the weddings? It's a very sad statistic, but no, obviously it was not these causing one another. The relationship here could be explained by a third variable, the economy. In the 30s, Great Depression, people no longer could afford to get married. They could not afford to live in general. So that was the cause of both of these relationships. So very sad example. I should probably include more happy examples for these correlations. The heroism examples, those are more happy examples, right? So this can be a problem if you have a graph like this, you have this data, you have this correlation, but you don't know what third variable is affecting it, right? Because weddings are not causing suicides, suicides are not causing the weddings. There's a third variable, the economy, that's causing both of them. So you can solve this problem partially from doing a thorough lit review, reading more articles, understanding the theory better of how these things should be related to one another, and then measuring those third variables. So you could have a measure of economy, or like, what is the socioeconomic status of these people that are getting married versus not getting married? What's the socioeconomic status of those people who are doing suicide or not doing suicide, right? So you could measure that directly. But if you haven't measured it, it might make you confused. Interestingly, for a while, because researchers were making this error, they were literally claiming that the lack of getting married was leading or causing men to commit suicide, which was not the case. It was the other variable of the economy. So we mentioned the directionality problem a minute ago. Let's talk about this here. So when two variables are related to each other, they can be related in many directions. It might be they're both related to each other. It might be A to B. It might be B to A. So that's what we're talking about with directionality. So the assumption is made that the change in variable A will cause a change in variable B. But the opposite could be true. Maybe it's that B is changing and then that changes A. And depending on how you're measuring it, if you're just measuring a correlation in a survey, you might not be able to, you basically can't tell if it's A causing B or B causing A. So correlations can't tell us really about the cause. They can pinpoint that maybe there's something we should investigate more here and see if there are causal relationships, but they can't really tell us those directions. So sometimes the directionality problem combines with the third variable problem. Maybe it looks like A and B are positively correlated, but really it's because variable C is causing both of them to increase at the same rate or something like that. So directionality can also add on with this third variable problem. So with that, if we have these misunderstandings of directionality and we just have correlational data, it might be that we are trying to treat symptoms rather than the causes of those symptoms, right? We want to be able to understand the actual relationship between variables. So correlational studies are very important to understand how variables relate to one another, but they're not really great at saying this A is causing B or what is it B causing A. And if we're focusing on symptoms rather than causes, we might be wasting funds. We might be supporting other things happening that we're not measuring. So let's get a more obvious example and a happier example than some that we've been talking about. How are volunteering and happiness related? So in your own notes, what do you think is the directionality between happiness and volunteering? So by that I mean, do you think as happiness goes up, more people volunteer? Or do you think as people volunteer, their happiness goes up? Or people that don't volunteer, their happiness goes down? or people whose happiness is already down don't volunteer? What is the directionality of this relationship? Pause the video really quick. Think about what you know about happiness, volunteering, if you have volunteered, and just put your own idea. What direction is this happening? Does happiness cause volunteering? Does volunteering cause happiness? Both in the positive and negative direction. So like more happy or less happy, more volunteering or less volunteering. That is what I mean by positive and negative. Like positive going up, negative going down. All right, hopefully you wrote down your ideas there from what you know. So let's see, does happiness lead to volunteering? Or does volunteering lead to happiness? What the actual case is that happiness can lead to volunteering. But then volunteering can lead to happiness. And happiness can lead to more volunteering, we see. So it's an example of a positive upward spiral. When people are more happy, have more positive emotions generally, they're more open to go and volunteer. But also, when they're volunteering, they'll probably be making new relationships. They'll see probably the work that they're doing as meaningful, and it will make them more happy. As they do that, as they're getting more happy, they'll be more likely to volunteer. So this is a positive upward spiral. So you're happy, you volunteer. As you're volunteering, you get happy. As you're happy, you volunteer more or continue volunteering. So there is that directionality. It's a positive upward spiral. So let's think about a few more variables here. We're adding a couple more. So how are self-esteem, academic achievement, and drug abuse related to self-efficacy? So we'll define a few of these. Hopefully academic achievement, and I think my next slides define self-efficacy and self-esteem, but not academic achievement or drug abuse. Hopefully drug abuse is already understood, abusing of drugs, using more than is healthy for you, that kind of thing. Academic achievement is like doing well in school, getting good grades, being attentive in school, those kinds of things. So what is the directionality? If we want to increase academic achievement and decrease drug abuse, what should we do? What should we aim for? Should we increase self-efficacy? Should we increase self-esteem? Should we decrease self-efficacy? Should we decrease self-esteem? What's the directionality here? So before I talk about the definitions, if you understand the definitions already, pause really quickly, maybe make a little diagram of which way do you think the arrows go between these. So self-esteem, for those of you who don't remember these terms, self-esteem is a global or general evaluation of yourself. So I like myself, or I'm happy with who I am, or I don't like myself and I'm not happy with who I am. So it's really general. It's a really global evaluation. Is your esteem of yourself high? Is it low? Are you happy with yourself? Are you not? Self-efficacy is different. It is the belief that you can master any situation and produce favorable outcomes. So, for example, if you had high self-efficacy in psychology, you would have a belief that you could do well in your psychology classes, on your psychology tests. If you had low self-efficacy in, say, math, you might have a belief that you can't do very well. You're not going to master this. You're going to have a really hard time. You're not going to be able to learn the things that you need to or do well on your tests. That would be low self-efficacy versus high self-efficacy. So really it's more like a feeling that you're capable of acting in any given situation. So statements like, I think I can, or I know I'll be able to do well on the exam, or I know I can learn this new dance, those are getting at self-efficacy. And so this is a separate construct from self-esteem. Again, self-esteem is that general, like, I like myself, I think I'm pretty good, or something like that. Maybe not good, because good kind of has a moral connotation. So I like who I am is self-esteem, versus self-efficacy is, I think I can overcome challenges that come my way. That would be self-efficacy. So self-efficacy, interestingly, grows when, so now that I've said the definitions of these things, so you know what self-efficacy is, you know what self-esteem is, you know what academic achievement is, you know what drug abuse is, what's the relationship of these things? If our end goal is to increase academic achievement, decrease drug abuse, what do? Do we work on self-esteem? Do we work on self-efficacy first? Does self-efficacy cause a change in self-esteem? Does Academic achievement cause a change in drug abuse? Does academic achievement cause a change in self-esteem? Does increasing self-esteem then increase academic achievement, which then increases self-efficacy? So there's a lot of ways you could put these four variables together. So in your own notes, just on some page, write down, how do you think these are related to one another? All right, so hopefully you've done that. I'll let you know what the research really shows. So self-efficacy increases when people feel they are capable of action and affecting situations. So when people see that they've been efficacious in a situation, their self-efficacy goes up. When people see that they were capable, that they did do well, that they could do a thing, their self-efficacy goes up. So teachers, parents, mentors, we can all scaffold middle, late children, even adults, to build capacities in lots of areas. So if you want to learn photography, you can build those capacities. As you see yourself getting more capable, self-efficacy goes up. So self-efficacy is often domain specific as well. So when I say like your self-efficacy will go up, it's probably going to go up in that specific area around, say, photography or psychology, knowing how to ride a bike. This video is fun and cute. I like to watch it anytime I think about it, but it might give you some suggestions of how self-efficacy is related to self-esteem. Again, self-efficacy can be domain specific. It grows when you see yourself actually being capable or being efficacious in situations. So if you think you can learn how to ride a bike, you're probably already fairly high on self-efficacy. As you actually do succeed to ride a bike, self-efficacy goes up. So while it can be domain specific, you can look at general self-efficacy as well. So if overall, in most domains, you have high self-efficacy, your overall self-efficacy score would also be high. All right, so let's watch this cute little video.
What, do you got any words of wisdom? What about for all the other kids trying to learn how to ride their bike? Can you say anything to them? Give me some thumbs up. Subscribe.
So great example of self-efficacy growing in that situation. You might have some ideas now of how might self-efficacy be related to self-esteem. So a statement like, I know you can get, if you keep practicing, you can get better and better. That's high self-efficacy. Saying something like, I feel happy of myself, that's very much self-esteem. So I'm happy of myself, self-esteem. If you practice, you can do it. That's high self-efficacy. So hopefully that gives you some suggestions of how these variables might actually be related. So how are they related? If we want to increase academic achievement and decrease drug abuse, actually this is the real relationship. As you increase self-efficacy in many domains, let's say math specifically, or science, or reading, you will see increased academic achievement. People will see, oh yes, I can do better in math. I can do better in science. I can do better in remembering to check if my recording is going. Right, so domain specific, you can do that. But then also, as you see that increased academic achievement, as you see yourself doing well academically, your self-efficacy will continue to go up. So there's this cycle happening here that self-efficacy is going up, academic achievement is going up, at the same time. So there's a cycle there. Interestingly, when that happens, then we see self-esteem go up. So as self-efficacy goes up first and you see yourself doing better, doing well, improving, then your self-esteem will follow. And also drug abuse will decline. So these are some variables that you can look at correlationally. And you might see, oh, there's a relationship between self-esteem and self-efficacy. There's a positive correlation there. When one goes up, the other goes up. But just from that correlation, you might assume, well, let's increase self-esteem and then self-efficacy will go up. But in reality, by doing more causal like experiments, longitudinal studies, what we find is that self-efficacy going up leads to academic achievement going up, and as those both go up in a cycle, then self-esteem goes up. So yes, those positive correlations might point us to there is some relationship between self-efficacy and self-esteem, but the causal relationship we can't find through just correlations. We have to do experiments and longitudinal studies to see what the pattern is of causes. So what's the direction? This is actually the direction. There's a nice positive upward spiral here. There could, if your self-efficacy was decreasing, you could also have negative downward spirals. But we're talking about positives here, so positive upward spiral of self-efficacy going up, achievement going up. As you achieve, self-efficacy goes up, and academic achievement goes up more. As those things happen, self-esteem goes up, and drug abuse goes down. So it is a more complicated relationship than what we've been talking about with just two variables. So if we feel we can do something, we generally try harder to then achieve it. So if our self-efficacy is up, we try harder and then we do achieve. And when we achieve, our self-efficacy continues to go up. So nice positive spiral there, really good example. But when we have a lot of variables that might be determining a relationship, how can we figure out what the relationship is? So let's say there's a behavior. Let's say we're in elementary school, we're an elementary school teacher. The children are acting up in class. That's the behavior we observe. So why is this happening? Maybe we come up with some hypotheses. Maybe theory suggests some ideas, and so we come up with some hypotheses. Maybe we also add some of our own. So we go to theory to make hypotheses, maybe come up with some of our own ideas. So one suggestion, maybe the kids are hungry. Maybe I am in an area and almost all my students are in poverty, so they're hungry when they come to school, and so they're acting up in class because they're just hungry. Maybe the school lunch doesn't contain proper nutrition, so another reason, maybe they're hungry, so they're acting up in class. Maybe they're just bad kids, right? Maybe that's the case. We should investigate, maybe that's the cause. Maybe this would matter if you're like switching classrooms in the day. Maybe the previous teacher has been making them work through recess. Maybe they're behind or something, and so these kids aren't getting to play before they come to my class. Or maybe my teaching's not engaging. Maybe that's why the behavior is the students are acting up, right? So there's all these possible variables that could determine the relationship. So first, we should rule out alternative explanations. So to do this, you can do experiments, and we'll talk a lot about that in a later chapter. But one way to rule out alternative explanations is to test them experimentally. But we're focusing on correlations today. So with a correlational study, you can use statistics to partial out or take out the effect of one variable on another systematically. Obviously, literally removing the effect of one of the variables in an experiment is a little better way to do that, but statistically we can do that, and it's pretty strong statistics. So we'll talk about multiple regression in a little bit. That's what we're talking about here, partialing out bits of the variance. So taking out the effect of one of the variables. So with multiple regression, we look at the relationship between multiple variables. So we might have one dependent variable or outcome variable and multiple independent variables that might be affecting. So in this case, our dependent or outcome variable is the children acting up in class variable, and our multiple independent variables in this case would be these yellow ones that we're talking about. Teacher making them work through recess, or my teaching's not engaging. So we need to figure out what are the relationships between all these variables so we can try to pinpoint what might be the strongest relationship, and that might suggest which is the cause. So a good example of multiple regression that might make more sense to you is how do age, weight, heart rate, what do age, weight, heart rate, and gender, what is their relationship with some variable? So this graph or this table is looking at your oxygen O2 max. I forget exactly what it was, like the quickness of taking in oxygen or something like that, or how saturated your lungs were with oxygen, something related to oxygen. But it's looking at these variables. Age, so the age you are you 12, are you 21? Your weight, are you 12 pounds, are you 21 pounds, or probably more likely for an adult human, something like 140 to 190 pounds, something like that. Then heart rate, what is your heart rate? Is it slow, is it fast? And then gender. So with this, gender is one that biological sex would probably be more relevant here than gender, but you could include a variable like that. So a demographic variable. You could include something like socioeconomic status. So you could look at multiple variables and how they are related to the variable you're interested in, like how much oxygen your lungs are taking in. So knowing all those relationships might be able to let you predict the outcome variable better. So might be able to let you predict, are the kids going to be acting out today? Am I going to get enough oxygen in my lungs? And so that could be really relevant for like some kind of medical procedure, right? So you might be able to predict, hey, this person is this old, this weight, this is their heart rate. So when they're under surgery, we should probably set the oxygen up to 10 rather than to 7, right? So that's how some correlations can be really, really useful when looking at them in these multiple ways, looking at the relationship between multiple variables together. That's what we call multiple regression. So another practical example that might make sense to you is many college admissions use calculations based on multiple regression to accept or reject students. So you'll often see things like, this is the cutoff. If you have a GPA lower than here, don't apply, or this is the average GPA for our students. This is like high school GPA or something like that. So you'll see some numbers maybe published. And oftentimes those kinds of numbers and the things that you're putting into the application, they basically put it into a multiple regression equation to then predict what your grade will be or what your GPA will be at the end of your freshman year. Some of them might also do like later years or something like that to try and predict, is this student going to have good enough academic achievement for the students we want to bring into this school? So you can predict someone's score using something like a regression equation. So let's start pretty simply, 2 variables. So you can see a correlation here. Maybe there is a correlation, a positive correlation between, let's say this is college GPA and this is ACT score. So those might be some things that, actually this should probably, for this example, this should be high school GPA, shouldn't it? So high school GPA, ACT score. So you're applying to Harvard, whatever school you're applying to this school, and you give them your high school GPA, you give them your ACT score. Maybe there's a positive correlation. So if you get a really high ACT score, you've also got a really high GPA. If you got a low GPA, you've got a lower ACT score. That's not how directly, it's not that strong of a relationship. But you can use those and then predict what will be your GPA after year 1 of college. So using ACT score, using GPA, put those in your regression equation, and you can predict what your, obviously to do this you would need that third variable for previous students, what was their final GPA, so it's just algebra basically, right? So you have your regression equation, and then based on our previous students who had that GPA and that ACT, this is the range of their GPA later on. You're using the equation that way. You can add additional predictor variables. So maybe you are trying to predict, I've got some of the language in here mixed up. So we're not actually trying to predict ACT score. We're trying to predict actually college GPA here. So we're using something like, our high school GPA and our ACT score. We're plugging those in to predict college GPA. So criterion variable is the variable we are predicting, in this case college GPA, and the predictor variable is like the ACT score, high school GPA. That's the predictors of the final variable, the criterion variable. So with that, you can use multiple variables in a correlation, correlate them all together, just like I didn't do any specific multiple correlation or regression with all my variables in the heroism scale one because I had specific hypotheses I was testing. But in the future, I could go back to that data and say, how are all these variables related to each other? Can I predict one using 3 of the other variables or something like that, right? So one thing that you'll often get for grad school of psychology, you'll give them your college GPA. You'll have your GRE score. You might have your psych GRE. You'll have recommendation letters. Those recommendation letters, they could give a quantitative scale to, right? So this isn't always done, but perhaps what the admission board does, maybe they read through this letter and say, on a scale of 1 to 10, how good is this recommendation letter? And then they average them all, right? Maybe scale of 0 to 10, this is a 7, but this one's an 8, and this one's a 9. So your average recommendation letter score is 8. So that's all plugged into this regression equation. And then they predict, well, what's your GPA going to be after year 1 of grad school? So not all of them do it exactly that way, but it's a very common way to get those initial, it's a very common and easy way for schools to get their initial kick out people. So anyone who doesn't get over the bar of this regression equation gets their rejection letter pretty quickly. So, but there could be other variables affecting this relationship. We call multiple correlation also multiple regression. It's making predictions from multiple variables. So rather than an R for correlation, we're talking about R squared. So if you see those statistics in your paper, so this one, the R squared or R squared, that's talking about multiple correlations, so multiple variables and the effect that one or more are having that we're measuring on the others, versus this is R for like a single correlation. So we can calculate those multiple correlation and pull out the effects of one. So we can pull out the effects of the teacher before us not letting them out to recess. So I have 2 videos here, multiple regression, especially the first time you hear of it, if this is the first time you're hearing of it. If you've done a stats class, this might be all understandable. I'm trying to get the concepts over. But I do have 2 videos I want to show. They are really stats heavy examples, but I want you to listen to the concepts. So it does talk about the stats, so that could be helpful to you if you already know a little bit about the stats, but really I want you to know the concept behind multiple regression. What is multiple regression actually doing with these correlations, and what can you do with correlations in multiple regression? So we'll start with this one, but focus on the concepts, don't focus on the math. If you understand the math, awesome. But focus on the concepts.
Stack quest. Yeah, Stack Quest. Hello, I'm Josh Starmer, and welcome to Stack Quest. Stack Quest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about multiple regression, and it's going to be
clearly explained.
This Stack Quest builds on the one for linear regression, so if you haven't already seen that one yet, check it out. Alright, now let's get to it. People who don't understand linear regression tend to make a big deal out of the differences between simple and multiple regression. It's not a big deal, and the Stack Quest on simple linear regression already covered most of the concepts we're going to cover here. You might recall from the Stack Quest on linear regression that simple regression is just fitting a line to data. We're interested in the R squared and the p-value to evaluate how well that line fits the data. In that same Stack Quest,
so this simple regression example, that's an example of just using our 2 variables to predict something. So using our, what was the first one we talked about? We talked about high school GPA and ACT score. That's an example of simple regression versus multiple regression. You're adding additional variables. So that's why it's called multiple.
I also showed you how to fit a plane to data. Well, that's what multiple regression is. you fit a plane or some higher dimensional object to your data. A term like higher dimensional object sounds really fancy and complicated, but it's not. All it means is that we're adding additional data to the model. In the previous example, all that meant was that instead of just modeling body length by mouse weight, we modeled body length using mouse weight and tail length. If we added additional factors, like the amount of food eaten or the amount of time spent running on a wheel, well, those would be considered additional dimensions, but they're really just additional pieces of data that we can add to our fancy equation. So from the stat quest on linear regression, you may remember the first thing we did was calculate r squared. Well, the good news is calculating r squared is the exact same for both simple regression and multiple regression. There's absolutely no difference. Here's the equation for r squared, and we plug in the values for the sums of squares around the fit, and then we plug in the sums of squares around the mean value for the body length. Regardless of how much additional data we add to our fancy equation, if we're using it to predict body length, then we use the sums of squares around the body length. One caveat is, for multiple regression, you adjust r squared to compensate for the additional parameters in the equation. We covered this in the stat quest for linear regression, so it's no big deal. Now we want to calculate a p-value for our r squared. Calculating f and the p-value is pretty much the same. You plug in the sums of squares around the fit, and then you plug in the sums of squares around the mean. For simple regression, p-fit equals 2, because we have two parameters in the equation that least squares has to estimate. And for this specific example, the multiple regression version of p-fit equals 3, because least squares had to estimate 3 different parameters. If we added additional data to the model, for example, the amount of time a mouse spends running on a wheel, then we have to change p-fit to equal the number of parameters in our new equation. And for both simple regression and multiple regression, p-mean equals 1, because we only have to estimate the mean value of the body length.
All right, so there was a lot of stats talk right there with the equation. If you followed it, it probably helped you understand. If you weren't following it, it might make you more confused, so I want to just go back to the simple example. Two variables here related to one another can let you predict. So if you have this line of best fit and you know the body length is here, you would predict probably the weight would be somewhere around here. Right? That's what you're using these for. And that equation lets you do that. Here, you're graphing three things. So rather than being two-dimensional, so like a flat, you're graphing this on a flat paper. Here, it's three-dimensional. So you have kind of a cube of data, 3 dimensions of data. So you have body length, tail length, and mouse weight. And so graphing that all together, this dot is the score on body length as well as mouse weight as well as tail length. So it looks like their score is 1 on body length, about 2 on tail length, and about 2 on mouse weight. Right? So that's what this point is showing. And so you're still finding a line of best fit essentially through all that data, but now it's in 3 dimensions, so it's within a cube rather than our correlations here are like this. So that's what you're doing as you're adding more variables, you're graphing them together, or honestly after 3 dimensions, you're letting a computer graph them together, and you're using this kind of equation to give you a good prediction of what's based on the variables that you have.
So far, we've compared this simple regression to the mean and this multiple regression to the mean. But we can compare them to each other. And this is where multiple regression really starts to shine. This will tell us if it's worth the time and trouble to collect the tail length data, because we will compare a fit without it, the simple regression, to a fit with it, the multiple regression.
So another way to say this, I want those words, so you can compare, hey, did adding tail length, did this make our prediction better, or did this make our prediction worse? This one has no tail length, so if we can compare the one with tail length, the one without tail length, this one has partialed out or has removed the effect of tail length from our measurement, from our prediction. So this is a really good example of you can take out tail length by taking it out of your equation, comparing the two answers and say, hey, did adding tail length, did that really help us? Should we have these 3 variables, or are these 2 enough? And it really depends on your hypothesis, your research questions. How you're going to use that and test that. Even if it's a very little bit of additional data, it might be a useful variable. Let's say you're trying to do something like shoot a rocket into a comet and see how much it changes something. That recently happened. They there was two asteroids orbiting another. NASA shot a spaceship into the other one, the smaller orbiting one, to see how much it changed its orbit. So with that, you might want to measure tons of variables that even have a very small effect in that case, versus in some cases, maybe just body length and mouse weight is enough for what you need, and you don't need that third variable. And this helps you look and see if that's something you need. With, again, just correlational data. Not causation, not experiments, it's just correlational data.
To a fit with it, the multiple regression. Calculating the F value is the exact same as before, only this time we replace the mean stuff with the simple regression stuff. So instead of plugging in the sums of squares around the mean, we plug in the sums of squares around the simple regression. And instead of plugging in p mean, we plug in p simple, which equals the number of parameters in the simple regression. That's 2. And then we plug in the sums of squares for the multiple regression, and we plug in the number of parameters in our multiple regression equation. Bam! If the difference in r-squared values between the simple and multiple regression is big, and the p-value is small, then adjusting tail length to the model is worth the trouble.
All right, so again, there were the stats in there. I think the stats are useful because they are explained simply, but for your purposes, you don't need to know those stats. I hope you're doing a better job at grasping these concepts, is what I'm hoping. So another video, similar, different data, different examples.
In the previous video, we discussed that a regression line is a line that best models the data, the line of best fit. For instance, here is a scatter plot of the data for passing yards and points scored. Here is the regression line, which is y hat equals 0.0753 times x plus 11.313. And it takes on the form of y hat equals mx plus b. In this example, we used one independent variable, x, or passing yards, to predict a dependent variable, y, points scored. And here is the table with the ordered pairs used to develop that regression line. But in this and many other instances, we can use more than one independent variable to improve the prediction model. In our table, we can add in rushing yards and say defensive points allowed. So
here, there were the 2 dimensions, just like our last example started with the 2 dimensions, but then they're adding a 3rd and 4th dimension. So you can't really draw that kind of graph, a four-dimensional cube, but that's what we're doing. We're mathematically adding on dimensions, and computers can do that calculation, they can do that graph, and they can check what is the relationship between all these variables and then compare. Is it better predicted? Is it more predictive when you include all these variables or only some of these variables? Are some of them not really having any effect? That's what you're doing with multiple regression.
now we have 3 independent variables, and we can construct a multiple regression equation. The equation for multiple regression is similar to the equation for a single independent variable regression line. It is y hat equals b plus m1 times x1 plus m2 times x2 plus m3 times x3 plus onto mk times xk, with k being the number of independent variables being used. So from our table,
So for that equation, you can just keep doing this as many variables as you have. So they're trying to look at points scored as y. I was mentioning there were 4 variables. They're using these 3 variables to predict this 4th variable.
we have passing yards, rushing yards, and points allowed as the x1, x2, and x3 variables. Calculating a multiple regression equation is a bit complicated, so I use this online calculator, inputting the y variable and the x1, x2, and x3 variables. And as you can see, the equation is y equals 7.3778 plus 0.0386 times x1 plus 0.0665 times x2 plus 0.3028 times x3. And the r squared, or coefficient of determination value, is 0.5582. So 55.82% of the variation in points scored can be explained by the multiple regression model. And we can use this equation to make
So what that's saying is that this model is using 3 variables, and it's doing a fair job. It's explaining about 55% of the variation in y based on these variables. So maybe if we added more relevant variables, we could get an even better prediction, get it up to like 70% prediction. But depending on your research question, depends, like, do you want to just know how much of this is affecting y, Or are you trying to explain 100% of something? Again, if you're trying to like throw a rocket or a spaceship into a comet, maybe you want to get as close as you can to 100% prediction. But maybe you're just saying, how much can we predict with the variables that we do have?
Predictions. For instance, if a team had 250 passing yards, 85 rushing yards, and allowed 21 points, we would plug those three values in for x1, x2, and x3, and the predicted points scored would be 29.04. All right, my friends, that would be the very basics on multiple.
All right, so hopefully that helps you understand with a couple additional examples how we can use correlations in psychology research. So again, we're taking all the variables that we're measuring in a correlational way, maybe through a survey or something like this, and then we're statistically looking at what are the effects of each variable by itself, all the variables together. That's what multiple regression is. So again, we can use multiple regression to look at the effects of each of these variables in the system. Again, we won't get that causal data. We wouldn't be able to see that first self-efficacy goes up and then academic achievement goes up and they go up together and then self-esteem goes up unless we do experiments and longitudinal studies. But we can see how the variables, how strongly each of the variables are interacting or correlated with each other, and if self-esteem is a really big part of this relationship or is it not a very big part of it. So multiple methods help too. This discovery wouldn't have been possible. You wouldn't see that causal relationship without the longitudinal studies we did. All right, let's talk about some other correlations too. When we're looking at correlations, these next few ones that I'm talking about are called heredity-environment correlations. So a relationship between genetics and your environment. So remember, correlation means relationship. It doesn't mean causation. So correlation means an association, a relationship between some variables. Correlation does not mean causation. So there's a couple different types of heredity and environment correlations: passive genotype environment correlation, evocative, and active genotype environment correlation, also called niche picking. So what is a passive environment genotype correlation? This is when the environment's just already supportive of the genetic predispositions of a child. So let's use a child as an example here. Let's say the parents, at least one of the parents, maybe let's just make it easy. Both of the parents already are really good with music. Let's pretend music ability, pitch or something like that is entirely genetically caused. It's not, just let's go for this example. So the genes of this parent already are really good for doing well with music. So they will probably set up an environment for the new children, for the offspring, that are already supportive of those genetic traits, right? So you'll have more musical instruments around the house, listen to music more often. So yes, you've got the genes for doing well with music, but your environment is already passively, you're not doing anything, your environment's already supporting those genetic traits. Let's pretend reading speed is 100% genetic. It's not, but let's just pretend. So if two parents have the genes for reading speed and they can read really, really quickly, well, maybe they have more books in their house. Maybe they've got a big library and they go to the library more with their kids, right? So the children are growing up passively in an environment that's already supporting their genetic traits. So that's an example of a correlation. The genes and the environment are related to one another in a way that the organism is passively experiencing support for their genetic traits. So that can make it hard to see, well, is this caused from the gene? Is this reading speed caused by the gene, or is it because their environment had a bunch of books in it? Is their music ability caused by the gene, or is it because they have an environment where there's musical instruments all over the house? So that's one reason that these heredity environment correlations are good to investigate, to see, well, what is, going back to like the nature nurture. So how much of it is which? In these examples I just gave, it was like 100% genes, but those are ridiculous, silly examples. Another type of gene-environment interaction or correlation is evocative. So this is when the organism or the child's characteristic elicit a type of environment. So them acting and their genes elicits responses from their environment. So an example of this is, let's pretend being friendly is 100% genetic. It's not, again, just an example. Let's pretend being friendly is 100% genetic. So the friendly child will probably get more friends. They will elicit more friendly behaviors from others because of their traits. They're being friendly because that's their genetic trait. Other kids will then be friendly with them. So they're evoking, they're changing the environment in a way that then is also supportive of their genetic traits, versus a child who doesn't have the gene for friendliness. Maybe they're always really grumpy, probably will have fewer friends. They're going to change the environment in a way that's maybe supportive of not having that gene. So, or uncooperative child. So this one is a little bit different. So we have the evocative, the behavior of the organism is changing the world around them. This one now, active genotype environment correlations. This is niche picking. When a child or an organism seeks out an environment that is compatible or stimulating for their genetic traits. So let's pretend ability to do parkour is 100% genetic. It's not, but let's pretend the ability to do parkour or gymnastics is 100% genetic. A person who has those skills, genetic skills, might seek out environments that support those skills. Maybe they'll want to go to gymnastics gyms or parkour gyms or go out and practice those things. So they will pick environments that support their heredity. And these kinds of things can make it difficult to pinpoint how much of any given thing is nature versus nurture. If your trait leads you to change the environment with the evocative, or you are already growing up in an environment supportive of your traits in passive, how much would we be able to pinpoint or partial out, that is, from nature versus nurture? So active genotype environment, again, you're picking a situation. Evocative, you are changing the environment, usually unintentionally. So that is something with multiple regression. You could try to partial out some of that data, but that's one thing with like the nature nurture. It can be difficult to pinpoint exactly how these variables are related to one another. All right, so what's another thing with correlations to think about? Well, what about the selection? Who are we sampling? Who are we surveying? Where is our data coming from? Are we choosing data in a random way or a non-random way? Are we representing all the people we want to talk about, or are we excluding people unintentionally? So this is a funny picture from a YouTube video I saw. This interview with Warren Buffett, Bill Gates, and I don't remember Munger's first name. But essentially, they came and they were interviewing these capitalists, these billionaires, about what's better, capitalism or socialism. So their selection was pretty biased, right? They picked capitalists to talk about capitalism versus socialism. So probably not the best sample to choose to get data from. Maybe have capitalists and socialists on the panel to discuss it or something like that, right? So that just kind of a silly example to show the group that you select is kind of important to answering your question, right? So if you want to get a sense of everybody at Salt Lake Community College, you should randomly pick maybe like 20% of everybody at Salt Lake Community College. You don't want to only pick psych students if you want to know about everyone at Salt Lake Community College. So this goes back to things that we've discussed before, like weird samples. So we need to pick people to sample from. Otherwise, our correlations and the relationships we find might already have problems at the methods part of this. So if you're picking from weird samples, so Western, educated, industrialized, rich and democratic, if you're picking from those samples but you want it to apply to the whole world, it might not, right? So you might find a correlation. You can do the multiple regressions, but it's still dependent on your methods. It's still dependent on your sample, who you have selected. So this is also relevant for if you have a voluntary study, like who is volunteering? What are the people that are volunteering? How are they different from the people who are not volunteering? A lot of my recent studies have used MTurk workers, so people doing surveys online for a little bit of money. What's different about them compared to the weird population? What's different about them compared to the world population? Is it more like the world population or less like the world population compared to college sophomores? Luckily, MTurk workers are a better picture of people around at least the U.S. than college student samples, so it is a little better sample like that. It does tend to be still a little lower income than the average in the U.S., but better than, say, college student samples. Then, if you're maybe asking a question about a Democratic leader, so a Democrat leader, so if you have a survey pop up on social media asking you about a presidential candidate for the Democratic Party, who's going to respond to that? What if it was a Republican leader, the Republican candidate for president? Who is selecting themselves into your data? Right? So I'll sometimes, especially right now, I'm recording this during a really close to November. So I'm getting ads on YouTube or Facebook or even Reddit in some cases about political officials running for campaigns, and sometimes it'll be a little survey. How bad is this person doing, or how good is this person doing? So while it's obviously like a biased question and it really wants to get you into like donate to their person, it's so funny. It's like, who are you trying to get to with this? And it's really obvious. But yeah, who would respond to the survey about a potential Democratic candidate for president? Who would respond to the survey about a Republican candidate for president? So you're going to get specific people who are or are not in your sample. So how do we solve all these problems? Well, the first thing is to have good methods. Make sure you do have good methods in your study. And a lot of this class, a lot of these weeks that we're talking about are how to do good methods. So you can have the statistical tests for correlation. Those are good, you use them properly, but you need to have good methods first. Your statistics are as bad as your data was, or your statistics are as good as your data was. So your final results are really dependent on the methods you use. So are you using valid measures? Are you getting at your survey of heroism, your survey of empathy, your ACT score? Are these valid measures? That's an important first question. What about your sample? Is your sample full of people that you actually want to be talking about? Or are you missing a bunch of people that should be included? What about correlation? Should you be using correlational tests? Should you be doing an experimental study? Are you needing to do an interview instead? So it depends what you want to know. The research question, your hypotheses, are really dependent on the methods you choose should be the best methods to answer your questions. And then you use statistics. You use the statistics to help determine the relationships that exist between these variables. And then you might do additional study to falsify any new hypotheses. So that is correlation. I'm going to go back to some of the basic first slides because we went all into the depth of multiple regression. Personal regression is not really a thing that I know of. So here, this is an example of correlations. So positive correlation goes up this way, negative correlation goes down this way. Here are some graphs of actual variables being related to one another. How closely is empathy related to social responsibility in this sample that I collected? Well, it's an R of 0.63, so pretty strong positive correlation. You can see the graph going up that way. Here you can also see the graph going up this way. So all of these are positive correlations. This one's really much weaker of a correlation compared to this one and compared to this one. Right? So you can look at these correlations, look at these graphs, and then the multiple regression is just adding on additional variables. So I could, if I wanted to, use basically 1, 2, 3, 4, 5. I could use maybe 1, 2, 3, these 4 variables, heroism, self-efficacy, moral courage, and social responsibility, to see how well I could predict empathy. Or I could do it like our example here with self-efficacy. see how it suggests the data is suggesting is self-efficacy more related to self-esteem or academic achievement, or is empathy more related to social responsibility than it is to heroism, those kinds of things. So correlations are really useful studies for examining how variables are interacting with each other. Again, correlation doesn't mean causation. There might be some causal relationships happening when things are correlated, but without doing things like experiments or longitudinal studies, we wouldn't know that, say, self-efficacy and academic achievement, they're both going up at the same time, and then because of that, self-esteem goes up, drug abuse goes down. If we just looked at simple correlations, we might say, oh, when self-esteem goes up, drug abuse goes down. Let's just work on self-esteem. Turns out that doesn't actually work to decrease drug abuse. Increasing self-esteem by itself does not have that causal effect. So we need to understand what our correlations can and cannot tell us. If our samples are good, if our methods are good, correlations can give us a lot of really great information, a lot of really great data. But again, that is data about relationships between these variables, but it's not causal relationships. When we get to the chapter on experiments, we'll talk a lot about causal relationships. Experiments are like the gold standard for getting at cause.